Back in 1992, I was asked to give a Mazursky lecture at LPSC, and I was not that long out of graduate school. And at that point, they wanted someone younger in the field and someone more senior to give the Mazursky lecture. And the other person who gave it with me was Gene Shoemaker. And needless to say, I was terrified, just terrified. I couldn't believe I was in the same room with Gene Shoemaker, let alone having to get up and actually speak before he spoke. So it was an entirely traumatic experience. To be honest with you, I really don't remember it at all. But what I do remember was how absolutely kind Gene was. He was really nice to me, very chatty, very supportive, and that was his personality. He was not just an amazing geologist, an amazing planetary scientist. He was a generous and warm scientist, especially to people who were junior in the field. So for me to give this lecture named after him is quite an honor. So thank you very much. Today, I want to talk a little bit about one of my favorite subjects, and that is comparative climatology. And it's a particularly critical subject, I think, right now for a number of reasons. The last of which I'll get to towards the end of the talk, which is the fact that all of a sudden, something that I certainly never expected when I began my career, we're actually on the verge of being able to do comparative climatology, not just with planets within our own solar system, but with planets from other solar systems. And so I think it's important to reflect back on the fact that we are from this particularly unique, amazing world in our own solar system, with this very fragile atmosphere and this very, very unique surface. But one that really drives us to go out into the solar system and say, what other planets can we study and how can we utilize that information to better understand our own planet? This has obviously become even more critical in the face of human-induced climate change, and this is just the deviation of average surface temperature just from the year 2012. And normally when I give a talk, I show a video that takes this from the late 1800s all the way to the present, but I figured, okay, the last thing I need today is a video that stalls and ruins my talk. So anyway, you're just getting 2012. You don't get to see the alarming fact, and I show this video whenever I give public talks, because to actually talk about climate change is one thing with the public, but I find to show them with their own eyes data that shows that this planet is indeed warming at an alarming rate is something that's incredibly important. And obviously when you also look at this map, you can see that that distribution of average surface temperature going up is not uniform across the planet. And, oops, that's interesting. And in fact, you could see from that map that those effects of climate change are intensified at the poles, particularly in the Arctic region, but also in the Antarctic, which makes it ever more critical that we use our assets that we have to try to study those areas to try to understand what's going on. Now, it's no surprise to most of you, and you can see up on the upper left there, that's the ice cover in the Arctic from last year. On the right-hand side is the ice cover in the Antarctic from last year. And what NASA's been doing to try to better understand exactly what's going on in those regions in the absence of having IceSat, we've been using an aircraft called Ice Bridge that had a town hall meeting today. And the results of it have been really scientifically amazing, but on the other hand also really scientifically depressing. I had the opportunity this fall, about 2 months ago, to go, actually it was a month ago, to go down and go with the aircraft that was based in Punta Arenas, Chile, and we flew down to Antarctica. And so these bottom two photos are ones that I took. This one of an area called the Fountain Lakes Ice Stream, and this is just the West Antarctic Peninsula that we flew over on the way back. But obviously the ice loss in this area, not to mention the ice loss that Ice Bridge and other assets have been measuring up in Greenland, and the transfer of that ice into the ocean is something that's of extreme concern, and that we really need to better understand over time. And obviously the effects of climate change aren't just limited to melting at the polar regions. As everybody who lives in this state, and certainly most people well know, that there's been an amazing drought, and even despite our last day here of not so great weather, The amount of rain we're getting certainly doesn't do much to address the drought that's taking place in California at this time. And this is just GRACE data of California showing the withdrawal in water out of the aquifers. And if you look at the recently released National Climate Assessment, you can see, at least for the US, that obviously region by region, the effects of climate change over the next 10, 20, 30, 40 years are quite variable. And certainly increasing drought is something that the Southwest has to be concerned about. So when you look at these issues, it puts a new urgency to me into the topic of comparative climatology. It's not just something we're interested in, but trying to utilize the planets to better understand how climates in general behave and evolve over time is a subject of quite importance. And so when we look at our own solar system and say, well, okay, where are we going to go to try to understand climate? Probably the two most obvious places are certainly our two companion planets here, Venus and Mars, but then obviously also somewhat unexpectedly going to Titan, one of the moons of Saturn, also can provide a great lot of information. Obviously, Titan is the only satellite that has a substantial atmosphere, and I'll get to why Titan is so particularly interesting in a bit. The other thing I like about climatology is it's actually something that brings together all of the disciplines that are here at AGU today. Because if you're going to understand climate, you really have to understand all the processes that are taking place on a planet. From how is the core behaving, how is that affecting the internal heat evolution of a planet, the volcanism on the surface, the interactions with the atmosphere, any biosphere that exists on the planet, all the way out to the top of the atmosphere and the effects of that atmosphere and its interaction or potential interaction with the solar wind. Obviously something I just saw Bruce. Obviously something that MAVEN is helping us address right now, that outer part of that climate puzzle is something that MAVEN is addressing at Mars. So all of these factors, it brings together in a truly interdisciplinary fashion all of the work that we do here at AGU. I want to first turn to Venus, and to me, Venus is often referred to as sort of Earth's twin gone wrong, and it is obviously quite a different planet than the Earth. If you look at a place that's 900 degrees Fahrenheit on the surface is dominated by volcanic features, and these are just a few of the range of types of features that we can see on the surface, from large volcanic flood fields to these large circular features called corona that are several hundred kilometers across, and probably formed by some sort of small plume feature, to large-scale volcanoes like this one that are several hundred kilometers across, several kilometers high. So there's an incredible range of volcanic features across the surface of the planet. And on Venus, without the pesky biosphere and all that water that we have here on the Earth, you have a much purer interaction of the interior of the planet with the atmosphere. So it's a particularly interesting place to study in comparison to the Earth. And indeed, there's been a number of models, especially those by Bullock and Grinspoon, going back to saying, the changing rate of volcanism has a huge impact on the atmospheric evolution of Venus and can help us understand a lot more about how the climate on that body evolved over time. Now, we have so many fundamental questions about Venus, and certainly one of those is there's a lot of belief that Venus did have an early ocean. How long did that ocean persist? And can we use Venus in a case to really understand what conditions were like on the very early Earth? But then on the other hand, what was it that caused Venus to go wrong? Was it just the fact that Venus was a little too warm? If you look at differences between the interior models, the one for the Earth here and one that Susmakar and I have suggested after a model, this one is a model by Cordio et al., the fact that Venus has at this point in time a very different interior to that of the Earth. And so it's gone through a different evolution, but at one point did it have plate tectonics early in its history? Certainly Venus right now, we think because of the lack of water on the surface that subduction's not possible, but maybe it was in the past, and can we see evidence of that from the surface? All kinds of really intriguing questions that we have about Venus, some of which I think the answer does lie within the Magellan data set, but others of which would necessitate gathering different data at Venus. The other thing that's particularly interesting about Venus is with its very dynamic atmosphere that we've been studying with Venus Express for the last several years, We'd certainly, though, like to understand more about the role of aerosols, the role of the clouds on Venus, and so it makes also a particularly good place to go to study those aspects of climate that would help us better understand, again, climate evolution overall, especially in comparison to Earth. Now, one of the, I think, most exciting things, this is, of course, I'm biased, that's come out of Venus Express, is the fact that the VERTIS data, the infrared spectrometer data, has shown us anomalies, high emissivity anomalies on the surface. You want the lights to come? Yeah, people can't see the slides. I don't know if there's any way to lower the lights.
Well, they're trying to, it's making.
Oh, right, they're recording it. So that means you can't see the slides, sorry. Oh, well. Well, there's a volcano up there, and I can act out the slides for you. What you would see, if you could actually see the slides, is, so the Venus Express data, there's high emissivity anomalies, and Sue Smirkar, Jorn Halbert, other people who are here at this meeting have done work with these anomalies, and it turns out that a lot of the high emissivity anomalies, which are only basically mapped in the southern hemisphere of Venus, lie directly over top of volcanic features. In this case, Iden Mons, which is in Imder Regio, and in this case, over a volcano and a corona down in Themis Regio in the southern hemisphere. So you have these high emissivity anomalies that are directly correlated with volcanism. Not only that, the high emissivity anomalies seem to sit right on top of what look like, in a stratigraphic sense, relatively recent flows. The best explanation for these high emissivity anomalies, if you look at all the possible causes of them, that they're likely caused by unweathered basalt. So to have unweathered basalt, this would suggest that these have erupted in relatively recent times, probably within the last several thousand years. Now that's exciting because even though Venus is the same size as the Earth, we would anticipate that it's potentially volcanically active. The question of exactly how volcanically active it is critical. And unfortunately, with the Magellan data, we didn't have any real ability to say, is Venus still volcanically active? So this VERTIS data has given us really the best data we've had so far and able to say maybe Venus has been active in a recent sense. And I stole these conclusions from Sue Smirkar. So because of these high emissivity anomalies, people rarely accuse me of not being loud enough. Okay. Because of these high emissivity anomalies, again suggesting that they're caused by unweathered basalt, if you combine these with the fact that these anomalies are on volcanoes that tend to be at hotspot rises, that also have gravity and topography signatures that would indicate that they're relatively young, and again, stratigraphically from geologic mapping, we're suggesting these features are relatively young. All of that points to the fact that Venus is still relatively volcanically active today. But the issue is that we can say, okay, just because we know Venus is volcanically active today, which is obviously, again, volcanism is so critical because on Venus especially, it is the main input into what affects climate on Venus. We still don't have any real ability to say what is the rate of resurfacing been in the past, how has that changed over time. There's several different theories, but unfortunately we don't have any way to easily constrain that history of resurfacing. And so that little sad face is mine, not Sue's, even though this slide came from Sue. The volcanism in the southern hemisphere does seem to be focused at hotspots. So while Venus might have a stagnant lid, which has been suggested by many people, it doesn't actually preclude the fact that you can have ongoing volcanism on the planet. And we think, Sue and I, based on various mapping that we've done, that there's on the order of about 10 plumes, which makes Venus actually not that dissimilar to the Earth. And again, what that implies for the interior evolution of the two planets is really interesting. But we do think that we see two scales of mantle upwelling, both a larger scale of mantle upwelling that's producing the hotspot rises on Venus, along with a smaller scale that's producing features like very large volcanoes and corona. So what exactly is going on, how that interior evolution is proceeding, and how that's ultimately affecting climate in the recent past on Venus and going into the future is something that we are actually would like to know but are lacking the data to be able to answer. Now, if we turn to Mars, Mars is obviously a much smaller planet, and so you can say, okay, it obviously couldn't have been volcanically active Not likely up until the current day, certainly not like Venus, where you assume it's got a lot more heat-producing elements in the interior. Venus is still geologically active. Mars is, in that sense, not likely to have still this dynamic process of volcanism interacting with the atmosphere, even though there's been some suggestion of relatively recent volcanism. Now, that being said, in the past, Mars was clearly very volcanically active. We have abundant evidence of that from volcanic flows all across the surface to large volcanoes. So if we're trying to get at this primary question that we have for Mars of what is the history of water on the planet, understanding this issue of when was Mars active, how long did that geologic activity persist, is critical for understanding the history of the atmosphere and thus the history of water on Mars. Now, really exciting results talked about last week for Curiosity. Identifying Gale Crater, as the Curiosity rover has been going over a series of what are interpreted to be stacked river deposits and then going into basically lake bed deposits. So obviously, as Curiosity continues up those layers in Gale, what we're really going to be looking for, and I know there's more exciting results that are going to be released this week from Curiosity, but what we're really trying to get at, and what we have the unique ability to do with the Curiosity rover, is actually now really get in there and start to say, okay, can I use these rock layers and what they're telling me about potential alternating wet and dry periods on Mars? Can I attach time frames to those so I can start really trying to constrain the models I have of how the atmosphere evolved over time when Mars went from being a wetter world to the dry and cold world it is today? Obviously, that question is particularly important when we're trying to understand if life evolved on Mars. How long was there a stable, wet environment that could have supported life? And that's the question that we have. And again, stay tuned for more interesting results from Curiosity later this week. You know, as a geologist, whenever I can, I always bring up this result from Curiosity because to me, it was one of the most exciting things that we've been able to do to date. The fact that we were able to use the SAM instrument in this slide is courtesy of Melissa Traynor. The fact that we were able to use the SAM measurement to do in situ age dating on another planetary surface. You know, when I talk about Venus and the frustration that we have in trying to understand the rate of resurfacing in the past, how that's changed over time, a huge frustration on Venus is because we have no ability to use the impact crater population on Venus to get relative ages. Hugely frustrating. Let alone be able to do the kind of work that we're now able to do on the surface of Mars and actually get age dates and start to say, you know, as a geologist, your whole desire is to say what happened when. And that when is critical. And again, getting back to the life question on Mars, this history of water, you just don't want to know it's there. You want to know how long was it there? How did those environments proceed? So really exciting results that we saw last year from Curiosity. Obviously, you can't ever talk about what's going on now without plugging what's going to happen next. And we're really excited about the instrument suite that was selected this past year for the 2020 rover. A lot of really interesting instruments that, again, are going to push further this question of the persistence of water on Mars, how that links to climate evolution on Mars, and I think we have a really strong instrument suite to be able to do that. We're also obviously excited from a different point of view in looking at two of the other instruments that are on Mars 2020. The first one is the new Medley package that will be the entry, descent, and landing package that will measure the conditions as Mars 2020 comes in. And the other one is MOXIE, which is the first in situ resource utilization experiment that will be done on Mars. And those two things are really important for taking the exploration of Mars to the next step. When you look at, these are just 5 of the 8 landing sites that we've had on Mars, but if you look at the history of the in-depth exploration of Mars that we've been able to do, starting with obviously flyby, then orbiters, then being able to land on the surface, being able to rove on the surface, the next critical step to me, and as I'm saying this as Cindy Greeley is here, as somebody who's a real field geologist, as Ron was, to be able to get out into the field and actually crack rocks open with a hammer, analyze rocks, is how I think we're actually ultimately going to be able to answer this question of did life evolve on Mars. Face it, when we find it, It's going to be the subject of a huge amount of debate in this community, because that's what we do as scientists, despite what the public often thinks, is we actually like to argue. We don't really like to agree with each other. And so this question of being able to say, did life evolve on Mars? Can we say it definitively? Can we really understand the implications? I think is going to take humans on the surface of Mars and a laboratory on the surface of Mars to be able to really answer these questions in an in-depth way. So I think including things like MEDLI and MOXIE on the 2020 suite is an important step forward. And I think it's important for the community to think about as we think about future Mars exploration. How do we continue to move forward as we did back in the time of Apollo as a joint community between human exploration and scientific exploration to get the science that we're trying to answer at Mars, but also move forward to ultimately sending scientists. And again, these could be people who are some of your students or children right now, get scientists on the surface of Mars. Now, going further out into the solar system to think about climate, you have to go to Titan. And obviously, Titan is a moon of Saturn, one of the larger moons in the solar system, but again, the only one with a substantial atmosphere, composed mostly of nitrogen, but with methane and ethane in the atmosphere, and being decomposed by solar UV radiation, forming all kinds of interesting compounds called tholins that rain down onto the atmosphere, form probably some kind of layer on the surface, and land in the lakes and seas. But obviously we have this ongoing methane-ethane cycle where it's evaporated up into the atmosphere, it forms clouds, and it rains onto the surface, the only other place in the solar system where it rains besides Earth. Now, obviously, there's a lot of evidence that Titan is a dynamic place, and if you look at this bottom set of images is from a paper that came out a couple years ago by Turtle and others showing that the surface after an apparent rainstorm, and that's actually a cloud, not an arrow. It's just shaped like an arrow. A cloud that came through after the cloud system dissipated, the surface had changed, it had apparently become wetted, and then gradually dried out. Again, evidence that Titan is quite dynamic. Now, for volcanic processes on Titan, that's certainly something that we've struggled with on the Cassini team to try to understand. Can we find good evidence that there's been volcanism in the past? There's a series of flow-like features in Hoti Reggio that we feel stand a good chance of being volcanic. Certainly one of the better examples is this feature, which is called Sotra Facula, which appears to be a volcano. This is actually a topographic high with an apparent caldera at the summit. And obviously there's also something that's producing very fine-scale organic material that's forming dunes that wrap around a lot of the equatorial region of the planet. And obviously when we landed with Huygens, we saw good evidence of river systems on the surface. But when we were able to use the Cassini radar to map the northern hemisphere of the planet, we were pleased to see the abundant lakes and now seas that we've been able to identify across this region. And you can see they fall into really two morphologic groups, the very large seas, Kraken Mare being the largest, Ligeia the second largest, and a lot of very much smaller, more or less circular lakes that have been a cause of great interest to all of us on the Cassini team because they really morphologically look like collapsed depressions, these very small lakes. But what is collapsing? Methane rain onto water ice should not produce karst-like collapse processes. So exactly what's causing these collapse features, we're not sure, but it's pretty clear some kind of collapse feature, some kind of collapse process is going on, at least to form these smaller lakes. Now, the distribution of liquid between the north and south poles, which is where it's stable, the humidity is enough that it's stable to have liquid on the surface, the distribution isn't uniform. You saw all those lakes I just showed in the northern hemisphere. If you go down to the south pole, Ontario Locus, which is only about 80 by 100 odd kilometers long, is the largest feature, and there's a few other smaller lakes, but there's almost no liquids near the south pole. But one thing we have identified near the South Pole, and these are outlined in red here, and I know this is really hard to see, but these very small lakes in the South Polar region appear to sit in what are larger basins. Odette Aronson and others wrote a paper a number of years ago suggesting that Titan undergoes a Kroll-Milankovitch type cycle due to its orbit around Saturn that would cause, over sort of a scale of tens of thousands of years, about 45,000 years, a major shift in volatiles between the North and South Pole, so that right now we're in a time period that's consistent with most of the volatiles being in the Northern Hemisphere. About 30,000 years from now, that'll switch around, and the volatiles should move back to the Southern Hemisphere. These apparent empty sea basins in the Southern Hemisphere appear to be consistent with that. Not proof of it, but at least consistent with that, that perhaps now we're in this dry period at the South Pole of Titan, moving towards a different cycle in the north. The morphology of Ligeia, and this is a beautiful digital elevation model that was put together by Randy Kirk, allows us to really start doing a lot more in-depth lake and geomorphology studies. And these are being done primarily by Alex Hayes and his students from Cornell. But Ligeia has a fascinating morphology that we can study because it appears to have a very transgressive morphology. It looks like the liquid has risen. There's really no evidence in this area, with the possible exception of this kind of blunt shoreline here. There's no evidence of wave action, which we actually saw down at Ontario Locus in the Southern Hemisphere. You can see deltas that appear to be wave modified. You can see a wave modified shoreline. At Ligeia, you don't see any of that. You see what appear to be more analogous to sort of tidal mudflats, suggesting that the liquid has come up in this region and is potentially continuing to rise. Now, we know there are winds at Ligeia in the Northern Hemisphere. We know there's been erosion. This is heavily eroded terrain around the lake, so you can start posing interesting questions of why aren't we seeing more wave-related features? What does that imply about the history of liquids, the history of erosion, and exactly how all these features are interlinking? Now, obviously, what you'd ultimately like to do is actually go there and to be able to land a probe, and this map was actually put together by Ralph Lorenz. And it shows if you landed a small boat, for example, in different places on the lake where it would drift to after about 3 months with possible wind directions there. So the idea of being able to say, okay, if we really want to nail down this issue of how climate has evolved on Titan, what is the interaction between the liquid surface and the atmosphere, how's the energy being exchanged, you actually have to go there, land in situ, and do a more detailed investigation. And again, going back to the comparative climatology aspect, if you think that we have all those processes are obviously having a huge effect on us here on Earth, the whole interaction between our own oceans, our own atmosphere, here's an opportunity to go test those theories, see how they work on a world with a different gravity system, different fluid, very different temperature. So when we look at these 4 worlds, obviously each of them is telling us something very different about climate. You have Venus, which is really this story of volcanism and volcanism's interaction with the atmosphere, how that affects interior evolution, how that changes over time, how that affects climate over time. You also have this ability to really look at the role of clouds, the role of aerosols in an atmosphere, and understand how that's affecting weather and climate. Mars is a different story. It's getting back to this issue of evolution of the atmosphere over time, but in the sense of trying to understand the stability of water, how long did it persist, and how did that transition from a wetter Mars to a drier Mars actually occur? A fascinating question that I think we're actually getting on the verge of being able to answer. Titan, obviously, again, the only other place in the solar system we can actually go to understand this liquid exchange between the atmosphere and the surface that's currently exchanging. So each of these worlds is telling us a bit of specific information that we can only get to by going to those places. And to me, this question becomes even a more fascinating one when you look at the fact, and this is just this little area here is the area of the sky that's the Kepler field of view. If you look back over the last several years, I saw Sarah Seeger give a talk about a year ago, and she made the comment that really, to me, was shocking. So if you go outside and you look up at the night sky, basically every star that you're looking at a planetary system. And that's what Kepler has been able to provide us. It's with the over 3,500 planet candidates that have been identified by Kepler. You know, it's just an astonishing number that we're going to be able to try to understand. And obviously the great thing about Kepler is also that these planets are in a very different size class than we've been able to study previously in this sort of Earth, super-Earth, Neptune size range. And not only are we able to identify all these planet candidates, but we've also with Kepler been able to identify a large number of planetary systems and compare those to our own 7 planet systems, 5 planet systems, 3 planet systems. So gathering all these data together, and as we move forward with the K2 mission, which has already made its first potential planet identification, I think, and then looking towards 2017 when we have the transiting exoplanet survey satellite that we hope over its lifetime will identify about 50 Earth-sized planets, we're really starting to build up this amazing data set of places that may have climates similar or to our own, or maybe more similar to Venus, or maybe more similar to Mars. But again, we're developing the tools to be able to actually go answer these questions. And obviously with the launch in 2018 of the James Webb Space Telescope, we'll be able to target some of those planets for studies of their atmospheres. And so as we turn back and really start asking, what is a habitable zone? How do we identify life? How will we look for changes in atmospheres, the characteristics of atmospheres of planets around other stars, to really start getting at this question of, is there life on other planets? Are there planets like our own around stars? It even, to me, makes it more urgent for us to look at these worlds within our own solar system, Venus, Mars, and Titan, and utilize that information to try to understand the range of conditions under which we can, which potentially habitable worlds evolve. Thank you. Okay, I talked too fast, so that means I have a lot of time for questions.
Well, let me ask a simple question, since I don't know much about the transiting exoplanet mission. Can you just tell us a little bit of it? Is it an explorer concept or something different?
Yeah, it's an explorer. It's a small class. It'll launch in 2017, and again, it's going to specialize in identifying about Earth-sized planets around other stars in a small area of the sky. It'll look very intensely and identify Earth-sized planets.
How does it differ from Kepler?
It's just the next generation after Kepler, but it was also able to fit into a much smaller cost class. No, that's really hard to see.
Jeff Cargill.
Yeah, you started out talking about...
Would you use the microphone for posterity, sir? It's in the middle there.
You started out mentioning the prospect that we're, close to the prospect of being able to do atmosphere spectroscopy or, studies of atmospheres around planets in other star systems, planetary systems. What sorts of things are being discussed in NASA that might make this possible to do?
The James Webb Space Telescope will be able to look at atmospheres. It's an infrared telescope, but it will actually look at it'll look at a limited number of potentially habitable planets. Moving beyond James Webb to the next generation of telescope, we're looking at things like coronagraph technologies that would even more be able to get at this question of atmospheric composition and better identify, allow us to have the technology to study atmospheres. Obviously we're still really far away from being able to directly image, but moving from TESS to James Webb and then on to the concepts that have been discovered for W1st, AFTA, which would be the next likely mission beyond James Webb, are the technologies that we're looking at. And then beyond that, the problem is with these things, you need bigger and bigger apertures, and then people are really intrigued by coronagraph technologies, so that's where the focus has been.
Please identify yourself.
Hi, my name is Smiley from Chapman University in Orange, California. Thank you for your talk. I guess the real general simple question is, why would we care about other planets' climates in terms of our climate or our planet, our Earth?
Well, in terms of caring about our Earth, certainly they're not going to help us understand, how to better combat climate change or any issue like that. To me, it's more gets at this issue, which is a fundamental question that drives so much of what NASA does, is this question of, are we alone? So if you're looking at the range of conditions under which one thinks that life could develop, we certainly have a bias that it's a water-based type world. And so when you start looking at atmospheres around other planets, you're going to be basically looking for water signatures, potentially things like methane. You're going to see, are there gases that are not in equilibrium with each other, so that maybe some kind of dynamic process is taking place. And so really when you're studying the atmospheres, what you're doing is saying, well, this is the best that we have in terms of being able to study how close are those atmospheric signatures to our own, and can that tell us about life. Now the climate question to me comes in is that when you think about how you get life on a planet, to me one of the factors we don't always talk about as much is stability. And to me, if you have conditions that are constantly changing, it's going to be a lot harder for life to get very complex unless it can quickly, sequester itself from whatever process is changing rapidly. So if you have a stable climate on a planet, there's a much bigger chance that the life could go from a very simple life form to something more like us, which is obviously in the long term a lot of people's interest, is where could we go in the solar system and potentially have some sort of evidence for more complex life.
Thank you.
Hi, Steve Ruff from Arizona State. I'm not familiar with the Virtus emissivity results, and I guess I'm trying to understand how high emissivity relates to, or is interpreted as, fresh basalt. Can you expand on that, or? Mm-hmm. Okay.
Yeah, so the emissivity signature is telling you something potentially about how fine-grained the material is, or potentially something about its composition. So the high emissivity, what we've been able to do is sort of rule out that it's a material property, that it's more likely to be something to do with the iron content, the content that you're seeing. And so this is work that was done by Jorn Helbert and also informed by Lindy, who's sitting near me and who can hit me if I answer this completely wrong, is that by looking, it's much more likely that there's a compositional variation that's causing the difference in emissivity. There's also low emissivity anomalies that I didn't talk about, and those mostly lie over the tessera. And there's a potential that some people feel that those are caused by, this is Hashimoto and others that have written this paper, that those are also caused by a compositional difference. In this case, maybe it's an inference that it could be more granitic in those areas.
Okay, thanks.
It's a paper by Smirkar et al. In Science that talks a lot more about it than I just did.
Barbara Cohen, NASA Marshall Space Flight Center. Ellen, I appreciated your answer as to why we care about this for comparative climatology for life on Earth, but can you just talk a little more about explicit links, more explicit links that we could make scientifically or even maybe politically to having some of these effects isolated for our global climate change models that we use on the Earth? So for example, the liquid atmosphere interchange or things like that. Are there more explicit links we can make to climate change on the Earth?
Well, a lot of the times when I've had people really challenge me in an audience, about CO2 and its role in an atmosphere, I always like to point out, I said, I could maybe understand you being skeptical, which of course I can't, but, I could, I'm just trying to be nice, right? But the fact is we have all these other planets to understand the role of CO2. We can look at Mars and look at its atmospheric composition. We can look at Venus. We can look at the Earth. So just having, I think, these planets to compare to. The fact that when you in the past, people have, and I've heard this from climate people, when you take models that were built to understand the Earth's climate and you apply them to other planets, a lot of the time they have broken in the past in interesting ways that allow you to go back and refine the model in a better way. And so that's one way it's already contributed. For example, if you also look at the studies of the ozone hole on Earth, that was actually motivated by studies of Venus. I talked about the aerosols on Venus. There's an unknown UV absorber in the Venus atmosphere we don't totally understand. There are, again, there's aerosols in the atmosphere. That's actually one of the bigger areas of uncertainty in terrestrial climate modeling, is the role of aerosols, the role of clouds. Okay, so let's go to Venus and study those things and then compare it back to the Earth. So there are very specific things that you can say, all right, is this going to, we already have a very good understanding of Earth's climate, but by having ways to compare it to other climates, we can push the science a little further.
Thanks.
Howdy, I'm Cecilia Sanders. I'm an undergrad from Harvard University. So you talked a little bit about the search for exo-Earths and exo-Venuses and exo-Mars, but we know within our own solar system that, like, between Jupiter and Saturn alone, there's hundreds of moons and moonlets. I was wondering if you could talk a little bit about the possibility of studying exomoons. So, like, what do we need in order to make some kind of observation of, like, even the rate of occurrence of moons in other parts of the universe, and, like, does that have some bearing on our understanding of, like, because our own moon plays such a big role in our climate, and Titan has its own atmosphere, and we know that it's possible to have still those interior and exterior interactions even without a substantial atmosphere. So, like, what do we need to study those kinds of worlds, I guess?
I think that's a fascinating question, and it's a great question, because if you look at, we always talk and focus when we're talking about life and atmospheres. We focus on the Mars question. But if you look at the other places we would go in our solar system to look for life, they're very much not in that kind of canonical habitable zone that we like to talk about so much. You go say Europa. All right, Europa's not in the habitable zone. It's nowhere near it. But a lot of people strongly believe that Europa is actually the most likely place in the solar system to go to look for life. You look at Enceladus, another place with a sub-liquid ocean that could potentially harbor life. And obviously Enceladus spits its ocean out to us, which hopefully Europa does also, allowing us to at least get some initial analysis of it with Cassini. You look at Titan, which you could say, all right, it's very cold on Titan, there's no water, but there is a liquid. Could you have life on Titan? It's not in our model of how we think, but let's push the boundaries a little bit. Those are worlds that we're not, that we're not thinking about right now. We're still, because of the technology that we have, because we're struggling to identify Earth-sized planets in a habitable zone, that's where we are now. But obviously, a lot of the planets that we're finding are larger bodies that are likely to be more like Saturn, like Jupiter, and they're likely to have large systems of satellites, many of which could be like Europa, be like Titan. And we're just really far away from the technology of being able to identify really small bodies like that. And of course, if they don't have an atmosphere like Europa, then we're kind of stuck. So again, you can turn that in a positive way and say, doesn't that make it really urgent to go try to answer that question in our own solar system? Let's go investigate these icy worlds and see what their potential for life really is. We don't know. But we have the technology to go find out right here in our own solar system. Let's go answer that. It's a cool question.
Cool. Thank you so much.
Hap McSween, as a way of illustrating further how everything fits together in this story of climate, understanding climate, I wanted to say something about sample analyses. One of the interesting things about Venus to me is because of the high surface pressure and high temperatures, it's a place where metamorphism is going on the very surface. And those rocks are reacting with the atmosphere and maybe even buffering the atmospheric composition. So even sample analysis bears on this particular problem. And I wonder if something similar might be happening on Titan, but in a very different temperature regime. But if the surface rocks might be interacting with the atmosphere as well as the liquid is interacting with the atmosphere.
Yeah, it's a fascinating question that is really puzzling us on Titan right now, because again, if the bedrock on Titan is water ice, and yet clearly there's some kind of material at the surface that's behaving in a way that's not behaving like we think water ice should be behaving. So what that material is it just a really thick layer of these organic precipitates from the atmosphere? It's maybe too thick for that. So maybe, maybe not. Is there some other reaction going on between the atmosphere in the surface that's actually changing the composition? These are all fascinating questions that we're, you know, a lot of people are giving that idea a lot of thought. And again, it certainly would push us to try to go back there to try to follow up on some of that, because it's fascinating. And there's things in the Cassini images that I think are just super puzzling.
Art Charo from the National Research Council. Looking at the planets that you've looked at and their magnetic field, any comments about the probability that other planets would have a magnetic field and the important role that could play or might need to have present in order for life to evolve?
You know, that's a great question, because obviously the whole issue of the fact that, you know, our own magnetic field is critical for protecting life on Earth. And when you go to Mars, there is evidence that in the past Mars did have a magnetic field. I'm going to get the mission wrong. Which was the one that it was?
Galileo.
The Mars Global Surveyor, thank you. Mars Global Surveyor showed maps of the magnetic anomalies on the surface. So we know Mars had a magnetic field in the past. Was it there at the time that we think life evolved? How did that play in? That's something that I think is going to be a really interesting question when we start actually being able to really assess whether life evolved on Mars, what the timing of it was. You know, how important potentially was that magnetic field at the time, I think is a fascinating question. Obviously, the fact that the surface of Mars is so heavily radiated at the time with the cosmic radiation, we think even affecting the upper few meters of the surface in terms of really sterilizing it, you know, that makes it tough right now. In terms of Venus, you know, the fact that Venus doesn't have a magnetic field, did it have one in the past? We have no idea. You would think so. Why doesn't it still have one? I think these are huge questions. So if you look at our solar system, you have 3 chances. Only one of them has a magnetic field. One had it in the past. How critical is that to the life question? I think, you know, again, that's why I think this whole, to me, the really big, interesting questions are hugely interdisciplinary. And to pull out one factor and say, this is the factor, no, you can't forget about things like the magnetic field is critical.
Hi, I'm Kaylee Johnson from Arizona State University. Thanks for your time today. I just wanted to ask sort of like a more broad question. How do you feel that research like this would enable us to go to some of these planets, and how do you, or in exoplanets, habitable planets, and how do you feel that the support from the general public on missions like this would help encourage this type of mission?
You know, I think that one thing that's been fascinating to me over the last several years is the degree to which, when you start talking about sending humans to Mars, how excited the public gets. And I think when you look at the commercial ventures that we've seen come forward, whether it's Mars One or it's, you know, SpaceX talking about wanting to put humans on Mars, when you look at our Orion launch last week that we were so excited about, where we did this first test of the capsule that's going to move humans beyond low Earth orbit. I think those messages are resonating with the public. I think the public gets really excited about it. You know, if you look at things like Interstellar, where, you know, yay, NASA was so, you know, we went underground and worked for no pay. I'm not sure I like the message there, but, you know, I think there is a lot of public support for saying this is something we would like to see humanity do. And I think that public support is out there. I think people are intrigued by the question of, are we alone? You know, it's a really fundamental question. And so if you can make sure you talk about it to the public in terms of, we're not just doing this for spin-offs, which are great, and for technology investment, which is great, but we're also doing it because we're trying to answer some hugely fundamental scientific questions about the nature and evolution of our own planet, about the nature and evolution of ourselves.
And then just sort of a follow-up, how would we sort of keep ourselves from doing to other potentially habitable planets what we've done to this one?
Yeah, that's why I'm actually against Mars terraforming. You know, we've already screwed up one planet. Do we really want to go screw up another one? You know, I think we should be learning from what we're doing to our own planet. You know, I've talked to so many people who say humans can't have that much effect. Yes, we can, and we are. and the effects of it that we see every day. I mean, there are streets in Florida that now have to be pumped out at high tide. You see the warming and the collapse of, the loss of ice in West Antarctic, the collapse of the West Antarctic ice shelves, the loss of ice in Greenland. Those effects of climate change are here right now. They're blatant, they're alarming. And obviously when you see progress like we have this past week in Lima, where you can say, okay, there's been some initial progress, we have a lot further to go. And I think for the scientists to be continuing to bear witness to what's happening and continue to talk about it is important, and to continue to show it, I think is critically important.
Thank you.
I'm Robert Logan from Grinnell College. I was wondering if a follow-up to that, if you could talk briefly about the NASA path to Mars, where there's sort of the asteroid capture and people have talked about going back to the moon. Are those steps along that path purely meant as more sort of technological test beds? Or could you talk about the role that the actual science that would be gathered on those sort of waypoints on the way to Mars would link in with these broader questions from a science standpoint?
At least to address, first of all, the asteroid retrieval mission, in that case, the science which is coming out and which has been great is the survey of near-Earth objects that's been ongoing, and that's where the science comes out in that concept. When you look at trying to go to Mars, there's amazing science that's coming out that's not our kind of science, but that we're doing every day up on the International Space Station. And the work that we're doing to understand the effects of microgravity on the human system, how to mitigate those effects, we actually are using some of that information to come back and help better deal with human health here on Earth. So that science that's been going on has been quite deep and ongoing. In terms of when you look at what the difficult challenges are going to Mars, certainly radiation is one, life support, but to me a lot of those are more or less swamped by entry, descent, and landing. And so when you say, here are the things I need to be able to do, I need to transport humans between Earth and Mars, I need to land them safely on the surface, I need to get them back up off the surface. You break that up into a series of technologies. How do I best test those technologies? Where do I best test those technologies? Is it at the moon? Is it at an asteroid? Is it at Mars? Can I do it here on the Earth? And that's what we've been doing over the last several years. So certainly the development of the tools, which isn't as exciting, but it's absolutely necessary. So the Space Launch System, which will be first launched in 2018, the Orion capsule test that took place this year, the first human launch with Orion and SLS will be in 2021. Those are all steps to say, okay, let's move beyond low Earth orbit. But then once we move beyond low Earth orbit, we have to say, okay, where are we going and what are we going to do? And those are the paths that we're still trying to work through. We're trying to break it up into a logical sequence of what are the chief technology challenges, how do we best tackle each one of them, and where do we both? And this isn't just a question for the U.S., and that's why we're working very closely with our international partners through the Global Exploration Roadmap process, where we sit down with over 16 spacefaring nations around the world and say, who's going to do what, when, how's it going to work? Because NASA can't do this on its own. It has to do it in partnership with all of our international partners. And it's an ongoing process.